Welcome to lesson 5. We look at moments and moments generating functions. Sometimes when we are finding the mean and the variance of a random variable, we might come across some distribution that are not easy to maneuver in terms of integrating them, because for continuous random variables, we said expected of x means integral from negative infinity to infinity of x, f of x, dx. But the form of f of x is sometimes tedious to work with. And for all the moments, this gives the first moment. For you to go to the second moment, then it means that you have to integrate over all values of x squared, then f of x. So this continues to complicate the operations you carry out on f of x. And in fact, in some calculations, like when you're getting skewness and kurtosis, you may require up to the third and fourth moments. So this means this becomes cubed, complicating it further. So the moment generating function helps us to obtain these moments easily without having to differentiate the original function. So the kth moment of a random variable, x taken about 0 or about the origin, is just abbreviated by expected of x raised to power k, like now in this x raised to power 2 second moment, first moment, and so on. Now, the kth moment of a random taken about the mean, because you can consider moments starting from the mean. We have moments from point 0, and we can consider the mean as our point, then we get moments from that point, is abbreviated by expected of x minus the mean raised to power k, and this one is now denoted again, is denoted by mu subscript k. The moment generating function mgf of a random variable is defined by mx of t. So mxt abbreviates the moment generating function of an expression, and it's obtained by getting the expected of exponential tx. So if you have a PDF and then you get the expected of exponential tx, then you are getting the moment generating function of that random variable. We say that an MGF of x exists if there is b greater than 0, such that the MGF, that is MT or MXT, exists, that is, there is a number that defines it, less than infinity, for t absolute values of t greater than b. That is, exponential of tx is actually using a Taylor series expansion, can be written this way. And MT is therefore expected of this, which is summation over all of these, then probability of x. And if you apply probability of x, then you get 1 plus t expected of x. Then you can see the first moment being shown in this expression. This is a function of all moments about the origin. So k, for k a member of natural numbers, the derivative of the MGF with respect to t at point t is equals to 0 gives you the moment, the kth moment about the origin. That can be proven. You know, mx of t, we've seen that is 1 plus expected of t, which is mu1, the second moment, the third moment, and so on. And this is a Taylor series, in form of a Taylor series expansion. And if you put t is equals to 0 to this expression, then you get the derivative of the MGF at point t is equals to the mean. So if you get the derivative, the second derivative of the MGF, and put t is equals to 0, then you get expected of x. And then if we have this and this, we can therefore be able to get the variance, which is the second moment about the origin, about the mean. The MGF of a particular distribution is unique, and we can recognize the PDF if we are given the MGF. So if you have the MGF, it is easy for you to detect the PDF from which it was derived from. Let's look at some examples here. First, the first example, you're given that the MGF of a random variable y, MT, we can talk of MT, MXT is equals to 1 over 6 exponential t plus 1 over 3 exponential 2t plus a half exponential 3t. we are requested to get the mean and the variance of y. But we've seen that if you want to get the mean and the variance of such, and you're given the MGF, you just need to get the derivative, the first derivative of x with respect to t, and then replace t with the 0. So in this case, then we are going to have the derivative of this is 1 over 6 exponential t plus 2 over 3 exponential 2t plus 3 over 2 exponential t, or exponential 3t. Then we replace t with 0. So to obtain this, if you have exponential of a function and you want to differentiate it, you just differentiate this and multiply with here, and then you just write what you have. Derivative of t is 1, so I multiplied 1 over 6 with 1. Derivative of 2t is 2, I multiply with 2 here. That's why I'm getting this. So if I put t is equals to, if I put t is equals to 0, then I'm going to have 1 over 6 exponential 0 plus 2 over 3 exponential 0 plus 3 over 2 exponential 0. So this is a sixth plus 2 third plus 3 over 2. That is the mean. For me to get the variance, then I need to differentiate a second time. So the first derivative of the MGF with respect to t, we got a 6 exponential t plus 2 third exponential 2t plus 3 over 2 exponential 3t. So I have to differentiate these a second time so that the second derivative of x at t will be equals to 1 over 6 exponential t. Then I have to differentiate this 2t with respect to t to get 2 multiplied by here. I get 4 over 3 exponential 2t, differentiate 3t with respect to t, get 3, multiply here, get 9 over 3 exponential 3t. Then I put t is equals to 0, I get a sixth plus 4 over 3 plus 9 over 3, which becomes 6. Then I have 1 plus 8 plus 18, which is actually 27 over 6, or 2 by 3, 9. Then, if I want to get the variance of x, which we defined as the expected of x squared minus expected of x, this one squared, this is the same as getting the second derivative of the MGF at t is equals to 0 minus the first derivative of the MGF at t is equals to 0 squared. So this becomes 9 over 2 minus, this was a sixth plus 2 third, which was 1 plus 4 plus 6, which is 11 over 6 squared. So this gives you the variance. So if you want the variance, you have to get the second derivative of the MGF at t, then minus the first derivative of the MGF at t is equals to 0 squared to get the result of the variance. So we have examples 2 and 3, and we also have some exercises for you. That is the end of lesson 5.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.